All right. Ok, mi sentite? Vedete la slide?
Sì, sì.
Ok, bene. Okay, let me first of all recap a little bit what we studied last time, the second part of the last lesson. So if you remember, we extended our isospin symmetry to include also the strange quarks. And so in the framework of a more general and more wide symmetry that we call the flavor symmetry. Okay. So in analogy with isospin, the flavor symmetry can be expressed by unitary global SU3 transformation in the flavor space given by this expression here, where U, as usual, is a unitary matrix. And now we have 8 different global parameters for this transformation. Global means that they do not depend on the space-time coordinates. And of course, 8 generators for this transformation, which are chosen to be the 8 Gell-Mann matrices that you see here, which are in a sense a generalization or an extension, if you like, of the 3 Pauli matrices. Now, the basis vector for this fundamental representation of SU3 flavor are these 3 flavor triplets, U100, D010, and S001, which, as we've shown last time, are simultaneous eigenvectors of lambda 3 and lambda 8. And as eigenvalues, you obtain the third component of isospin and the hypercharge. Now, we can arrange these quark triplets or anti-quark triplets in the plane spanned by the third component of isospin in the horizontal axis and by the hypercharge in the vertical axis. Okay, so we obtain this representation for the quark triplet and this representation for the anti-quark triplet. And then we can combine them to create the multiplets of mesons. So we know that mesons are Q-bar states, bound states. So we can combine the quark triplet with the anti-quark triplet, and based on group theory, this results in an octet of states plus a singlet, okay, which is completely flavorless. And then we can have actually 2 octet states for low-lying states. Low-lying means essentially ground level states, the lighters, essentially, those coming with L equals 0. And we have indeed the pseudo-scalar mesons with JP equals 0 minus, which are these 8 objects here, and the vector meson with JP 1 minus. Okay, so here we have, for instance, in both cases, 2 pairs of isospin doublets. One is here, one is there, or also here and there. Then we have a triplet of isospin, which are the piots in this case, and the row mesons in this other case. And then we have also these additional states, 8, 8, and phi 8, which come with also vanishing third component of isospin and hypercharge. And then we have also analogous states for the singlet state. Okay, so we also have the eta 1 and the phi 1, but as we discussed last time, the eta 8 and eta 1 are not observed in nature, although they are predicted by the quark model. Okay, and instead what we observe is a combination of those, which we call eta and eta prime. Okay, and this combination is only possible between a state of octet and a state of the singlet, because the SU3 flavor symmetry is not an exact symmetry, it is a broken symmetry. And this allows you to mix states from the octet and from the singlet. And the same holds, of course, even at an even higher level for the vector mesons. Also, in this case, we do not observe the phi 8. What we do observe in the phi 1, we observe a combination of those two that we call the phi and the omega mesons, okay, which are related by these rotation matrix, so this mixing matrix, through the phi 1 and phi 8. And in this case, the mixing angle is even larger, is 35 degrees compared to the 11 degrees for the case of the pseudo-scalar mesons. Now, so all this was about the mesons, and then, okay, I will not repeat here, but we also derived some phenomenological formulas for calculating the masses of the mesons, which include these chromomagnetic interactions, so the spin-spin interaction, and these results in different values for the mass for the scalar mesons and the vector mesons, if you remember. So having said of that, let me go on now. And today we will discuss about baryons. So baryons, as you know, are bound states of 3 quarks, and the low-lying baryons, so the lightest, involve only up, down, and strange quark. In total, they come in 27 flavor combinations, and they all have L equals 0, so they are all low-lying. Their multiplet structure can be obtained by first considering the combination of the first 2 quark triplets, and then by adding the third one. So let's see how this works. Let's first consider the combination of the first 2 quark triplets. Okay, so one here, one is there. When you combine them, group theory tells you that you obtain a fully symmetric sextet of states, so 6 states here, plus an antisymmetric triplet of states. Okay, so this is what you obtain when you combine 2 quark triplets. Of course, in order to make baryons, we have to combine these with an additional quark triplet, okay? And so when you do so, it is equivalent to multiply this result by this addition, to combine this result by this additional quark triplet. So essentially, you have to sum the combination of the sextet with the triplet plus this triplet with the other triplet here. And this is depicted here, okay? So you combine the sextet with the new triplet plus the other triplet with the new triplet. So when you do the first combination, you obtain a decuplet of totally symmetric states plus an octet of mixed symmetry states. Let me remind you that mixed symmetry means that these states are symmetric only for the exchange of the first 2 quarks. But there is no asymmetry if you change the first with the third or the second with the third. And when you combine now these 2 quark triplets, you obtain another octet, which is now mixed asymmetry states, okay, plus a totally antisymmetric singlet. So overall, when you combine 3 quark triplets in order to create the baryon multiplets, you obtain a fully symmetric decuplet of states, 2 octets, one is a mixed symmetry and one is mixed asymmetry, plus a totally antisymmetric singlet. Okay. Now we have to compare this prediction with what we indeed observe experimentally. Okay. Let me first make this remark here. So when the quark model was proposed by Gell-Mann and Zweig back in 1964, there was an empty spot here in the decuplet. So all these particles were already observed at accelerators, but there was a particle here which was predicted by the quark model, but that was not detected at that time. Okay, and it is a very peculiar particle because it must have 3 strange quarks. Okay, S, 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 and so of course it must be heavier than all the ones that you see here. Yes. Oh, okay. I thought there was a question. So the discovery for this baryon that today we call the Omega Manus occurred at Brookhaven National Lab in the same year by using a huge hydrogen bubble chamber and a kaon beam. So you see here the picture for this decay, for this reaction actually, that was taken at this bubble chamber during this experiment. And here the full chain of decays is represented clearly, that you can already see here from the original picture. So essentially you have a beam of kaons, okay, coming from the bottom, that interact with a proton, so one of these hydrogen, the nucleus of one of these hydrogen atoms inside the bubble chamber. Then in the reaction you get 3 objects, Omega minus, okay, this new observed baryon, a K plus, which is bent by the magnetic field, and a K0, which is neutral, so it does not leave any track on the bubble chamber. Then your Omega minus decays into a Xi0, which is neutral, and a pi minus. The Xi0 further decays into a lambda 0, okay, and a pi 0, which are both neutral, so they don't leave any track in the detector. But then they both decay into, so the photon, the pi 0 into 2 photons. Sorry, yeah, one is here and one is there. So this is the pi 0. One is gamma 1 and gamma 2. The pi 0 decays immediately. And each photon further creates a pair of electron-positron, which are bent into the magnetic field. And then the lambda 0 further decay into a proton and a baryon. So this is the full chain that you also see depicted here. So a rather impressive picture. So at the end, the prediction of the quark model was correct. Okay. So indeed, the discovery of this new particle with the predicted mass and the predicted quantum numbers, okay, of course, provided very strong support to the quark model. Now, the 10 totally symmetric flavor combination of the baryon decuplet are depicted here. So we have isospin quadruplet. Okay, these delta objects are essentially excitation of the nucleons, and they only contain up and down quarks, as you can see. Okay, and they sit here in the decuplet. Then we have an isospin triplet, the sigma star minus, sigma star 0, sigma star plus, 1, 2, 3. Then we have, which have pairs of light quark plus a strange quark. Then we have the two psi minus and psi 0 star, which only have one light quark and two strange quarks. And then finally the omega minus, which is 3 strange quarks, which is of course an isospin singlet, having not U nor D quarks. Now, let's see now indeed what we observe experimentally. So experimentally, one observes indeed a decuplet of baryons with quantum number JP 3½ plus, this guy here, okay, and an octet of baryons with quantum number JP 1½ plus. Of course, we are limiting ourselves to the low-lying states, okay? And this is indeed in striking agreement with the predictions of the quark model. Okay, so all the quantum numbers, all the masses, everything essentially coincide with the prediction of the standard model to a very good precision. Let me make two remarks here. So as you see, we have a positive parity in both cases. Okay, plus and plus, and this is of course derives from the parity of the baryon structure. We know that it is a 3 quark object, so it is a -1 to the LQ1, Q2 plus LQ3, and then we have the product of the 3 intrinsic parities, which are all positive because we have 3 quarks indeed. So this is a factor 1, and this is just a factor 1 also because we are talking about low-lying states with L equals 0. So this is why the parity of all baryons, of all low-lying state baryons, is positive. And as we also noted for the case of the mesons, the quark model foresees the existence of one decuplet, 2 octet, and 1 singlet, as you remember. And the non-observation of the other octet, because we observed just one of those, and also the non-observation of the singlet, is a consequence of the QCD dynamics, which restricts the physical possibilities to only those with an antisymmetric color wave function. So this point is a very important point, and we will understand better next week during the in the QCD chapter when we will study quantum chromodynamics. So quantum chromodynamics essentially forces the color component of the wave function of baryons to be antisymmetric. And by this restriction at the end results in the non-observation of the other octet and of the singlet, flavor singlet. Okay. So this table summarizes the low-lying baryons, low-lying state baryons. So we have the proton, which is the lightest. We suppose it is stable, but we don't know. As we discussed last time, there are searches for proton decay into a pi plus, into a pi 0 and positron, which might reveal a possible potential violation of the baryonic number, if you remember. Then we have the neutron, which is just the isospin partner of the proton. It is a little bit heavier, just 1 MeV above that, and decays weakly into the proton, plus an electron neutrino, as we will study during the weak interaction chapter. Then we have the lambda 0, which is an isospin singlet. Okay, this decays weakly into a nucleon pion. Then we have the isospin triplet of the sigma baryons. Okay, all these guys decay weakly except for the sigma 0, which decayed electromagnetically. And you also see here the decay time is completely different compared to the others. Okay, much shorter. And then we have the 2 psi, which decays again weakly into a lambda plus a pi. These are the baryons from the 1/2 plus octet. And then we have, of course, those from the decuplet. So we have the 4 delta states, okay? And all these guys you see here, they the first 3 actually decay strongly, okay? And they decay into the members of the octet. So conserving strangeness. The exception, of course, is the omega minus at the end, because this has 3 strange quarks, so it cannot decay into a lighter baryon with 3 strange quarks, because this is the lightest baryon with 3 strange quarks. So the only possibility for the omega minus to decay is through the weak interaction, so by violating strangeness conservation into baryons with a different value of the strangeness. Okay, and you see here the corresponding branching ratios. So, of course, so far we have considered only the low-lying states, L equals 0. However, hundreds of mesonic and baryonic excited states have been discovered with non-zero orbital angular momentum, so L greater than 0. And also, these objects are also organized in successive SU3 multiplets and can be considered as excited states of the low-lying states. So the low-lying states, in a sense, they can be considered as the ground state for both baryons and meson states. Okay. Now, as we discussed for the mesons, also for the baryons, we have to deal with the mass of these objects. Okay. So you see in this table the measured mass of the baryons from the octet in the first column and those of the baryon from the decuplet. And you see also the number of strange quarks that are involved. Now, while particles lying in the horizontal lines, so here, etc. So the isospin multiplets have almost the same mass as one would expect due to isospin symmetry, which is only barely violated, okay, due to Coulomb effects. The masses in consecutive horizontal lines differ by a factor of 130, 150 MeV over C, as you can see. Okay, there is a jump every time you add one strange quark here. So these mass differences are due indeed to the relatively high mass of the strange quark with respect to up and down, and clearly the mass hierarchy reflects the number of strange quarks in the states. Okay. So as soon as you add a strange quark in your baryon, your mass will jump by a quantity order 130, 150 MeV. Then, as we already noted for the meson case, if SU3 flavor symmetry were exact, the mass of all the baryons within the octet and of all the baryons within the decuplet should be the same. Okay? But it is clearly not the case, as you can see already from this table. Okay, so similarly to mesons, the difference between the masses of the octet and of the decuplet baryons is due to the chromomagnetic interactions of the individual quark pairs. Okay, so also in this case, the difference between the octet states and the decuplet states is in the spin. We have 1/2 here and 3/2 there. And the different spin reflects in a different impact of this spin-spin interaction in the strong potential through this chromomagnetic interaction, okay, which is a phenomenological, can be treated phenomenologically, okay. So we do here essentially the same thing that we did for the mesons, but it is a little bit more complicated because we have to consider the 2x2 combination of 3 quarks in this case, okay. So we have to sum this expectation value 3 times because we have 3 possible permutations, okay? And so these results to be, so the sum of these expectation values results to be -3/4 for the octet states, so spinning 1/2, and +3/4 for the spinning 3/2, so for the decuplet states, where one can obtain this value much like the same way we did for the meson case. So we have first to square these, and then to extract the scalar products, and then to take the expectation value, okay, as we did. Of course, the only difference is now that you have to take into account all the 3 possible combinations. And so at the end, one obtain again a phenomenological mass formula for baryon, okay? So the mass of a baryon is given not only by the sum of the mass, the 3 constituent mass, okay? But we have also this term, okay, which requires spin-spin interactions, 1, 2, 1, 3, 2, 3, divided by the corresponding mass combinations. This coefficient, A prime, as usual, as we saw already for the mesons, is the product of the alpha strong, so the coupling constant for the strong interaction, times the wave function squared at the distance 0. Okay, so essentially this corresponds to the probability that 2 of the 3 quarks are at the same place, because as if you remember, the chromomagnetic interaction is only relevant at small distance. Okay, and a good agreement with the measured masses is found using the following values. So these are the following values for the constituent masses of the up and down quark, which are assumed to be equal. This is the constituent mass for the strange quark, and this is the experimental value of the parameter A prime. So this is obtained by fitting experimental data with this mass formula, essentially. Now, it turns out that these constituent masses are different, are actually higher than those that we need to describe the mass of mesons. Okay, if you remember from last lesson, the constituent mass for the up and down quark was around 300 MeV. Now we are around 360. And for the strange quark, it was 400. Now we are of the order 550 GeV. Okay. So this, however, should not be a surprise, because of course the QCD environment within a baryon is different than within a meson. They are different objects, okay, also from the QCD interaction point of view. And so this results in a different dressing of your bare quarks, okay, in the 2 cases. And this is why in the case of baryons, you can describe your data only if you assume higher values of these constituent masses. Okay. So of course, the quark model is a phenomenological model. Okay, it is based on a broken symmetry, although a relatively good symmetry. So it is not an exact theory. Okay, and so we have to arrange your parameters in order to reproduce your experimental results. Now, in these tables, you see now for all these octet and decuplet baryons, the comparison between the mass calculated theoretically from the mass formula that I just shown before and the experimental value. Okay, and you see that also in this case, as we already saw for the mesons, the agreement is strikingly good. Okay, we're using a very simple phenomenological formulas that only include QCD by dressing properly the mass of the quarks, okay? But there is nothing formal there about the color interaction, for instance. Nevertheless, you get a very, very good agreement with the experimental values, okay? So, as we already said for the low-lying mesons, there's a simple phenomenological formula provide a very good prediction also for the low-lying baryon masses, okay? And this is indeed another important success of the quark model. Any questions? Okay, no questions. So let's go on. Now, we have described the multiplet structure of baryons. Okay, we compared what we observed experimentally with what we can be predicted by the quark model. Let's now go into some more detail about the structure of the wave functions of baryons. Okay, so the wave function of baryons is obtained by combining the SU3 flavor wave function component with, as usual, the spatial component, the spin component, And in addition, one has to include also the color wave function component, so the one that depends on the color degrees of freedom, okay? Where color is, as you know, is the charge of the strong interaction, as we will study next in the course. So overall, the wave function of baryons must be given by a combination of the spatial component, the flavor component, the spin component, and the color component. And since we are talking about baryons, we have to require that the overall wave function must be anti-symmetric under exchange of any two quarks. Okay? Baryons, of course, follow the Dirac statistics, Fermi-Dirac statistics. Now, there is, however, a delicate point here that I want to highlight. So for the cases where the flavor wave function describes the equal particles, so up, 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 or down, 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 or strange, 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 the requirement that the total wave function is anti-symmetric is clearly a direct consequence of the Fermi-Dirac statistics. Okay, it is quite obvious. However, it is less obvious that this should also apply for the case, for the general case with different quark flavors. So suppose we have a baryon with the UDS. Okay. Still, although the flavors are different, one has to require that the total wave function is anti-symmetric with the exchange of any two quarks. And in this case, this arises from the combination between the Pauli exclusion principle and the SU3 flavor symmetry. And this is not a trivial subject. So the proof of this is provided in quantum field theory, and is based on the algebra of creation and destruction operators. It is not trivial, and it goes beyond the scope of this course. Okay. So for what matters us, let's just take this as truth, okay? So whatever is the flavor composition of your baryon, the total wave function of your baryon must be antisymmetric. So let's look now into more details into these components, okay? So the spatial wave function is symmetric for low-lying state baryons. Because if you remember, the symmetry of the spatial wave function is just given by -1 to the L. But since we have L equals 0 for low-lying states, then it's always +1. So this component here of the wave function is always symmetric for low-lying states. What about the color? The color wave function of baryons must be always antisymmetric. This we will study next week, okay, in the QCD chapter. So for the moment, let's take this as again as a truth. Okay. So this must be symmetric. This must be antisymmetric. The total must be antisymmetric. So what remains here? So the combination of the flavor and the spin. This must be symmetric in order for the total to be antisymmetric. So for low-lying state baryons, this can only be formed from totally symmetric combinations of the spin and the flavor wave function under the exchange of any two quarks. So once more, we have to require that the total wave function is antisymmetric for baryons. We know that this is symmetric for low-lying states. We know that this is antisymmetric. Actually, we will learn next week that this is antisymmetric. So the only possibility is that the combination of the flavor and the spin wave function must be symmetric. And let's see how we can build symmetric combination of the flavor and the spin wave function. So let's first of all discuss about the spin. So you know very well that when we combine two spin 1/2 objects, okay, we have two possibilities: either one spin singlet state, which is antisymmetric, or one spin triplet state, which is symmetric. Now, since we are dealing with baryons, we have to combine 3 spin doublets, okay? And what you obtain by group theory is that you obtain a quadruplet of fully symmetric spin states. So the spin is 3/2, and then we have the 4 projections, +3/2, +1/2, -1/2, -3/2. But then you also get 2 doublets, one with mixed symmetry and one with mixed asymmetry. Okay, so they are both 1/2 plus or minus 1/2, but we have a different symmetry properties. Well, let me remind you once again that the mixed symmetry means a symmetry under the exchange of the first and the second particle, or the first and the second spin state, but not the first and the third, or the second and the third. And similarly, mixed asymmetry means that it is anti-symmetric under the exchange of the first two particles, but not for the other combinations. So our goal, if you remember, is to build up a symmetric combination of the spin and flavor wave function components in order to get the full wave function to be anti-symmetric. Okay, and this can be actually obtained in two ways. The first way, which is the most obvious, is by combining the symmetric flavor decuplet state with the symmetric spin 3/2 state. So this guy here. Okay, so symmetric times symmetric give you symmetric. Okay. So one possible combination is to combine the decuplet, okay, so the 3/2 plus baryon states together with this quadruplet spin state. The other, less obvious combination is to combine now this mixed symmetry, either for the spin and for the flavor. So mixed symmetry and mixed asymmetry flavor octet states together with the mixed symmetry and mixed asymmetry spin 1/2 states, those guys here, okay? So in this case, we have to combine now the barians of the octet, which have spin 1/2, with these two mixed symmetry objects here, combinations here. There is in principle another possibility, okay? But if you remember, when you create your baryon multiplets, we also obtain a fully antisymmetric singlet, okay? However, it is not possible to construct a totally symmetric flavor times spin wave function from the antisymmetric flavor singlet, because there is not a corresponding antisymmetric spin singlet, as you can see here. Okay, if there were here an additional fully antisymmetric spin singlet, then you could also combine those two and get another possibility for your wave function, but this is not possible, because you do have a singlet for the flavor component, but you don't have a singlet for the spin component. Any questions? Is all clear? Am I going too fast, maybe? Hello? No, ragazzi, mi sentite?
Sì, sì, tutto chiaro.
Ah, va bene, ok. Senza un feedback mi sembra di parlare da solo a volte. Va bene. Vabbè, allora, se è tutto chiaro, adesso questo concetto qui, so what is in this slide, let me just summarize on the board. So let's move on here. Ok, vedete la lavagna, giusto?
Sì,
prof.
Bene. So, let me repeat again. So, our total wave function for the Barians must be antisymmetric for the reason that we explained before. Okay, so essentially as a result of the Dirac-Fermi statistics. But this is given by the combination of a spatial component times a flavor component times a spin component times a color component. Okay, so we know that the total must be antisymmetric. We know that for low-lying state, the spatial is symmetric. We will learn that the color wave function component is must be antisymmetric for baryons. And so what we need here is that this combination here is symmetric. And so indeed we have the two possibilities. So those that concern the decuplet states, so the 3/2 plus, for those cases, we combine the symmetric flavor component, because the decuplet states are symmetric for quark exchange, with the corresponding symmetric spin component, that is the 3/2. Okay, and so overall here you get a symmetric combination of flavor times spin. Now, if one considers instead the octet states, okay, one has to remember here that it is only required that the product of the flavor and the spin component is symmetric, but not necessarily individually. Okay, so indeed one can obtain a symmetric flavor spin combination by combining this mixed symmetry and mixed asymmetry flavor and spin component in the following way. So it's 1 over square root of 2, and then we have the mixed symmetry flavor component times the mixed symmetry spin component plus the mixed asymmetry flavor component times the mixed asymmetry spin component. Okay, and once you do this, you obtain at the end, as we will see in the example of the proton, a symmetric, again, flavor times spin component. So these are the only two ways you can combine spin and flavor wave function components to get, at the end, an overall antisymmetric baryon wave function. So in the slide before, I showed you the mixed symmetry state for the spin, but of course we have the analogous for the flavor that are the one that enters here. So this one here and this one here. So let me write them explicitly. So the mixed symmetry flavor are state with idle spin 1/2 and third component -1/2. And these are -1 over square root of 6 to d du minus u dd minus d u d, and I 1/2 I3 equal plus 1/2. This is 1 over square root of 6 to u d minus u du minus d u. So these are the mixed symmetry. So these essentially remain unchanged if you swap the first and the second quark flavor. And then we have the mixed symmetry, the mixed asymmetry, sorry, states. So again, this is I 1/2 I3 equal minus 1/2. And it is given by 1 over square root of 2 u d minus d u d, and I equal to 1/2 I3 plus 1/2, and then you have 1 over square root of 2 u d u minus d u u. Okay. So let's now make use of all these notation to really build up the wave function of the proton, in particular the proton with the spin up. Okay. So this is of course a notable example of a quark model wave function for a baryon, but of course the same methodology can be used to create any wave function of any baryon. Okay, pretty much using the same way. So what we need for our proton or neutron wave function, so this of course holds for both proton and neutron. Oh, sorry, I have to take a new page. Okay. So the wave function for proton and neutron, okay, for the spin and flavor component altogether, these can be obtained as 1 over square root of 2, and then we have, as we've seen before, the spin. Okay, now the order is different, but that doesn't matter. The spin and the flavor mixed symmetry plus the spin and the flavor mixed asymmetry states. Okay, and this must be, as we said, symmetric for exchange of any two pairs of quarks. So let's work out the first pair, okay, the first product. Okay, let's consider spin up proton. So spin up proton wave function. So the psi spin mixed symmetry times the psi flavor mixed symmetry. We have just to combine the two corresponding wave function components that I was just showing before. So for the spin, we have 1 over square root of 6, 2 up, up, down, minus up, down, up, minus down, up, up. And this must be combined with the corresponding mixed symmetry flavor wave function component. That is 2 u u d minus u d u minus d u. As you can see, the structure of these two objects is identical. It's exactly the same. You just have to exchange the up arrow with the up quark and the down arrow with the down quark. Otherwise, the algebra is exactly the same. So now let's combine those two. So we obtain 1/6, and then we have 4 u up, d down, minus 2 u up, d up, u down, minus 2 d up, u up, u down, minus 2 u up, u down, d up, plus u up, d down, u up, plus d up, u down, u up, minus 2 u down, u up, d up, plus u down, d up, u up, plus d down, u up, u up. So let me call the first one equation 1 and this equation 2. Okay. So this is the combination of the first two, so the first term, so the combination of the first two wave function component, and it is, you can check yourself, it is still symmetric for the exchange of the first two particles. Let's now do the same for the mixed asymmetry states. So phi spin mixed asymmetry times the phi flavor mixed asymmetry. In this case, we have 1 over square root of 2 up, minus down, up, times 1 over square root of 2 u du minus du u. Again, the structure of the two is identical. We just have to exchange an up arrow with the up quark and down arrow with the down quark. So let's take the combination of these two. So this is 1/2 u up, d down, u up, minus d up, u down, u up, minus u down, d up, u up, plus d down, u up, u up. And this we can call 3. Okay, I need another page, so just tell me when you're done, and then I will make a new page.
I'm okay, Prof.
Is everybody okay?
Yes.
Okay. So now, of course, we have to add the two and to put equation 2 and 3 into equation 1. Okay. So let's go here. So our combined spin times flavor component, okay, for the proton up, with spin up, we can maybe write it like this, okay. Then will be 1 over square root of 2. We are substituting into equation 1. Okay, now we have to add the two things properly. So this is 2/3 u up, d down, minus 1/3 u up, d up, u down, minus 1/3 d up, u up, u down, minus 1/3 u up, u down, d up, plus 1/6 u up, d down, u up, plus 1/6 d up, u down, u up, minus 1/3 u down, u up, d up, plus 1/6 u down, d up, u up, plus 1/6 d down, u up, plus 1/2 u up, d down, u up, minus 1/2 d up, u down, u up, minus 1/2 u down, d up, u up, plus 1/2 d down, u up, u up. Okay. Now we have to add all the terms that are homogeneous. So in particular, this guy add up with this guy here. Then this guy, let me put a double spray to sum up with this guy here. Then we have this guy here, 1, 2, 3, add up with this guy here, 1, 2, 3. And then this guy here, 1, 2, 3, 4, add up with this one, 1, 2, 3, 4. So let's make now these very simple additions. So the result is 1 over square root of 2, and then you have 2/3 u up, d down, minus 1/3 u up, d up, u down, minus 1/3 d up, u up, u down, minus 1/3 u up, sorry, u down, d up, plus 2/3 u up, d down, u up, minus 1/3 u down, u up, d up, minus 1/3 u down, d up, u up, plus 2/3 d down, u up, u up. Okay. And then we have just to reorder these terms to get our final result, which is the wave function of the spin-up proton. Okay, so let me just reorder these terms in the proper way. spin times flavor. So these we can write in a more convenient way as 1 over square root of 18. And now we have 2 u up, d down, minus u up, u down, d up, minus u down, u up, d up, plus 2 u up, d down, u up, minus u up, d up, u down, minus u down, d up, u up, plus 2 d down, u up, minus d up, u down, minus d down, no, d up, sorry, u down, u up. And this is our final result. Avete copiato tutti? Are you all okay? Okay, then let's summarize these back on the slide. Okay, so this is our result, okay? So at least for the flavor spin component, the wave function for the proton with spin up is given by these two, by the sum of these two combinations that are put here explicitly, and then after some trivial algebra, we end up with this expression that you can write even in a more compact way, because the other two set of 3 terms you can obtain just by series permutations of this first term here. Okay. And of course, what about neutrons? Well, neutrons, the structure is of course the same, and you can trivially obtain these by simply exploiting the isospin symmetry. So by simply exchanging the up quark with the d quark. Okay, so you take the proton wave function, you exchange the up with the down, and you're done. So this is now the wave function for the neutron with spin up. Okay, and of course, the wave function of the other hadrons, baryons, sorry, of the octet can be worked out similarly. Okay, we can make a 10 minutes break. So if you don't have questions, we can resume at 10 past 10. Okay? Okay, we can start again. So let me share. Ok, mi sentite e vedete le slide?
Sì, prof.
Sì. Okay. Okay. So so we just derived the spin flavor part of the spin-up proton wave function based on the quark model. Okay, so essentially on the simple idea that the proton is made by 3 quarks, 2 up quark and 1 d quark, and they should come in the proper combination in order to fulfill the symmetrization of the wave function. Now, there is and we also learned before that both for mesons and for baryons, the quark model provides very precise values for the masses based on the simple phenomenological mass formula. So this was indeed a very great success of the model itself. There is another sector of the hadron physics where the quark model provides, again, very valuable results and very valuable predictions, and this is the sector of the magnetic moment. Okay, so we have already introduced the magnetic moment for Dirac particles. Let me just repeat a few things that we already discussed. So if nucleons were point-like Dirac fermions, okay, the magnetic moment would be given like this. So for a Dirac particle, it is G, okay, which is the geomagnetic factor. This is the electric charge in units of the electron charge. Then we have the mass, and then the spin operator here that we can split into h bar half and the Pauli matrix. Okay. Then for the case of a Dirac particle, G is exactly 2. Okay. At leading order, at least. Okay, as we've seen in QED. And so overall, you can express everything for the Dirac particle in terms of the nucleon magneton. Okay, so for a Dirac particle, the magnetic moment is 1 nucleon magneton, then multiplied with the Pauli matrix, where the nucleon magneton is defined here. Okay, and of course we are using G equal 2. Now, however, the measured magnetic moments of protons and neutrons are substantially different from this prediction. So they are not just one magnetic nucleon, nuclear magneton, sorry, but for the proton it is 2.79 μn, and for the neutron it is minus 1.9 something μn. Okay. Of course, this is not a surprise because we know that the protons and neutrons are not point-like Dirac fermions. Okay. And these anomalous magnetic moment arise, of course, due to the composite natures of protons and neutrons, and can be explained the framework of the quark model in terms of the magnetic moments of the individual quarks. And this is what we are now going to do. So what about quarks? Quarks are indeed Dirac fermions. So for quark, we know that G must be equal to 2. They are point-like spin 1/2 particles satisfying the Dirac equation, so they are Dirac fermions. And the operators of the total magnetic moment and of the Z component of the magnetic moment for quark is given by these relations here, where QQ is the fractional electric charge of the quark in units of the electron charge. This is the constituent mass, and then we have the spin, either the total spin or the Z component. So let's move on now to the whiteboard. All right. So let me write again the Z component operator of the magnetic moment for quarks, which are indeed fundamental Dirac particles. So we have the electric charge in terms of the electron charge divided by the mass and Sz. Okay. Let's consider now, as an example, spin up quarks. So spin up quarks. Okay, so where now the eigenvalue of the third component of the spin must be plus h bar half. And so let's calculate now the expectation value for the up quark spin up magnetic moment. So this is U up, then we have our operator, and then we have U up, U spin up. Now we substitute the expression above for our operator, and we put outside all things that do not depend on the wave function, so the charge of the up quark and its mass. And then we have u up, the spin operator along the z direction, and u. And then we can substitute these with the numerical values of the charge and mass and of the charge, and also the expectation value for the spin of u quark. So for the charge, we have plus 2/3, as you know, for the up quark. Then we have electron charge divided by the mass of the u quark. And then the expectation value of the spin in the z direction is h bar half. This we can write in a more convenient way by multiplying and dividing by the mass of the proton. So this results in plus 2/3. Then we multiply and divide by the mass of the proton. So we obtain mp divided by mu. And then here we collect e h bar divided by 2 mp. Okay. And now we recognize here that this is the nuclear magneton. So after all, we can write our, okay, let me put it here, the magnetic moment of the spin up u quark as plus 2/3 the mass of the proton divided by the mass of the u quark, the constituent mass, times the nuclear magneton. Okay. What about d quarks? Of course, we can do the same exercise. So for the d spin up quark, we have d up mu z d up, and it is now the charge of the down quark, E divided by the mass, the constituent mass of the down quark, and then we have d up sz d up. The charge is minus 1/3, as you know. Then we have E mass of the down quark, and then we have the spin projection h bar half. And again, we can write this in terms of the nuclear magneton by multiplying and dividing by the mass of the proton. So this is minus mp divided by 3 mass of down quark, E h bar divided by twice the mass of the proton. That is, the magnetic moment of the spin up d quark is minus mass of the proton divided by 3 times the mass of the down quark times the nuclear magneton. Of course, in case of spin down, the eigenvalue for the z component of the spin operator is minus h bar half, and so one would obtain mu of u down as minus 2/3 mass of the proton, mass of the u quark, nuclear magneton. And similarly for the down quark, mu d down, mass of the proton, 3 times the mass of the down quark, and then mu n. In this case, we have a plus sign because we have 2 minus signs to be multiplied. Okay. And just that you know that if one assumes that the mass of the up quark is similar to the mass of the down quark, then one obtains the relation between the two. That is, mu u is almost equal to minus twice mu d. Okay, so this is about quarks, but now we want to build up the magnetic moment of the proton, okay, in terms of those of the quarks. So let me go back now to the slide. So in the quark model, the total magnetic moment of a baryon, or in particular the proton, is given by the vector sum of the magnetic moments of the 3 constituent quarks. So Q1, Q2, Q3. And therefore, the expectation value of the magnetic moment for a spin-up proton, for example, okay, can be written in this way. where you split essentially your Z component magnetic moment operator for the three constituent quarks, up, up, and down, that constitute the proton. Okay, and this has to be embedded with the proton wave function that we derived before. Okay, so this is our proton wave function for the flavor and spin, which are the only two components which are relevant for the magnetic moment. Okay. So, of course, we have 9 terms here, 9 terms there. So when you take all the cross product, you obtain at the end 81 terms here, okay, which is a crazy expression, of course. However, due to the orthogonality of the quark flavor and spin state, all the non-diagonal terms are 0. So all the terms where this side is different than this side, they are all 0, okay? So overall, we at the end obtain only the 9 diagonal terms, okay, which are the only non-vanishing. So let's now do this. All right. So let's write down now only the 9 diagonal non-vanishing contribution to the proton magnetic moment. Okay. So mu p, when you put there the full wave function of the proton and you make all the products, etc., and you neglect the vanishing terms, you obtain something like this. So 4 divided by 18. Now we have u up, d down, mu z, u up, d down. This is the first diagonal term. Now the second, 1 divided by 18, u up, u down, d up, mu z, u up, u down, d up, plus u down, u up, d up, mu z, u down, u up, d up, plus 4 divided by 18, u up, d down, u up, mu z, u up, d down, u up, plus 1 divided by 18, u up, d up, u down, u z, u up, d up, u down, plus 1 over 18, u down, d up, u up, u z, u down, d up, u up, plus 4 divided by 18, d down, u up, mu z, d down, u up, plus 1 over 18, d up, u down, mu z, d up, u down, plus the last term, 1 divided by 18, d up, u down, u up, mu z, d up, u down, u up. Full stop. So these are all the 9 diagonal terms, which are the only non-vanishing terms. Now we can make use of the expectation values. So let me write down the expectation values. So for u up, mu z, u up, the expectation value is plus mu u. For the u down, mu z, u down, the expectation value is minus mu u. Then we have d up, mu z, d up, the expectation value is plus mu d. And finally, d down, mu z, d down, the expectation value is minus mu d. And so we can substitute now. So we obtain mu p as 4 divided by 18, and then we have mu u plus mu u minus mu d plus 1 divided by 18, mu u minus mu u plus mu d plus 1 over 18 minus mu u plus mu u plus mu d plus 4 divided by 18 mu u minus mu d plus mu u plus 1 over 18 mu u plus mu d minus mu u plus 1 over 18 minus mu u plus mu d plus mu u plus 4 divided by 18 minus mu d plus mu u plus mu u plus 1 over 18 mu d plus mu u minus mu u plus 1 over 18 mu d minus mu u plus mu u. Okay, now we can simplify all things that cancel here. So these cancel with these cancel with these with these with these, those two here and those two there. And so you just have to arrange these terms, okay? So there is some very trivial algebra that I will skip, and at the end you end up with 4 divided by 3 mu u minus 1/3 of mu d. This is our final result. Ok? C'è qualcuno che deve ancora copiare?
Io ci sono, prof.
Ok, se nessuno deve... insomma, deduco che ci siete tutti. Torniamo alla slide. Okay, so let's resume our result. Sorry, not that. Okay, here we are. So for the magnetic moment of the proton, okay, we can write this in terms of the magnetic moments of the up and down quark in this way, in the framework of the quark model, okay? So with a very simplified description of the proton in terms of only two quarks, up, up, down, etc. For the neutron, again, one can exploit the isospin symmetry, so you don't have to do the algebra again, but you just have to substitute up quark with down quark and vice versa. Okay, so this is the corresponding expression for the neutron. Now, the best agreement between the quark model prediction and the measured values of the magnetic moment for low-lying state baryons is obtained by using these values for the constituent masses. Okay, so 338 for the up, 322 for the down, so they are slightly different, and 510 GeV for MeV for the strange quark. Okay. Now, when you use these values here, okay, you can now compute the magnetic moment of the up and down quark by using the formula that we derived before in units of the nuclear magneton. Okay, so when you just substitute the mass of the proton and the mass of the up quark for the down quark, and you multiply by the charge, you obtain plus 1.88 for the up quark and minus 0.97 for the down quark. Okay. Now, the only thing that remains to be done is to substitute these two values here, okay, to get finally the magnetic moment of the proton and that for the neutron. Okay, and once you do so, okay, so you just apply this formula here and substitute these two values, you obtain exactly the anomalous magnetic moment that you measure experimentally, the one that I showed you a few slides ago. So 2.79 for the proton and minus 1.91 for the neutron. Okay. And this is indeed another impressive success of this simple quark model. We can compare now the situation for all the other baryons, low-lying states at least. So here we have in this column the experimental value for the magnetic moments, okay, for all these values here. And here is your prediction for based on the quark model, okay. And you also see here how to write down this magnetic moment in terms of those of the quarks, okay, for each of these baryons. And now you can compare the experimental value. You can compare the experimental and the prediction, and you see that they do agree incredibly well. There is one of these baryons that requires some comments, that is the lambda zero. So the lambda zero baryon is a UDS object. Okay, it contains an up quark and a down quark whose spins are coupled to zero, and so they contribute neither to the spin nor to the magnetic moment of the baryon, the up and the down quark of the lambda. Okay, and therefore both the spin and the magnetic moment of the lambda baryon are determined solely by the strange quark. So in other words, one obtained that the magnetic moment of the lambda zero corresponds to the magnetic moment of the strange quark, as you see here. And this is the value that you obtain by using this value for the constituent mass. So let's calculate this as an exercise. So calculate the magnetic moment of the lambda baryon in the framework of the quark model using the following values for the constituent quark masses. So up and down are the same to this value, and then the strange is this one here. So let's do this. All right. So this problem 5.9. So the lambda zero is an UDS object in the framework of the quark model, okay? And it is an isospin singlet. Therefore, the flavor wave function for the UD pair is antisymmetric. So let's restrict ourselves to the flavor component for the UD quark pair. Okay, since it is an isospin singlet, this guy must be an antisymmetric object, like UD minus DU. And as a consequence, in order to have a symmetric combined flavor and spin wave function, also the spin wave function must be antisymmetric. Okay, so the spin of the up and down quark must form a spin singlet. So as a consequence of the lambda being an isospin singlet, also we have a constraint on the spin component for the up and down quark. This can only be an antisymmetric singlet state, so it can only be up, down, minus, down, up. Okay, and since this is an antisymmetric singlet state, the U and the D quark contribute neither to the spin nor to the magnetic moment of the lambda baryon, as I was mentioning before in the slide. So the spin and magnetic moment of the lambda can only depend solely on the remaining S quark. Okay, so let's first of all construct the combined wave function for the up and down quark, and then we will add the strange quark afterwards. So the flavor wave function for up and down times the spin wave function for the up and down. This will be 1 divided by the square root of 2. Then we have ud minus du times 1 over the square root of 2, up, down, minus down, up. And so this we can write in an equivalent way as, so we can combine the two, of course, as u up d down minus u down d up minus d up u down plus d down u up. Now, of course, we need the wave function of the lambda, so we have to add to these, to combine with these the remaining strange quark. Okay. So for the lambda in the spin-up state, this S strange quark must also be in the spin-up state. So the wave function will be something like this. So this is exactly what we have been written before. So u up, d down minus u down, d up minus u down d up plus d down u up, and now you adapt the S up here. So overall, this is going to be 1/2 u up d down S up minus d up u down S up minus u down d up S up plus d down u up S up. Okay. Now, once we have the wave function, spin flavor wave function for the lambda, we can compute the magnetic moment, much like the same way we did before. So let me take a new page. So the magnetic moment of the lambda 0 is defined as usual as the lambda for spin up, mu z lambda 0 up. Okay. Now, of course, we will neglect all the non-diagonal terms, which are vanishing, and we will only consider the diagonal terms. So this is going to be 1/4 u up d down S up mu z u up d down S up is the first diagonal term, plus d up u down S up mu z d up u down S up plus u down d up S up u down d up S up plus d down u up S up d down u up S up. Now we can substitute the eigenvalues, the expectation values, sorry. So this can be written as mu u minus mu d plus mu s plus mu d minus mu u plus mu s plus minus mu u plus mu d plus mu s plus minus mu d plus mu u plus mu s. So we can now cancel all things that cancel. So these. So all the contribution from the up and the down quark, which come with opposite sign, they all cancel. And so we remain only with the contribution from the strange quark, as we were announcing before. So this is just 1/4 times 4 times the magnetic moment of the strange quark. And in fact, this indeed corresponds to the magnetic moment of the strange quark only. These we can write in terms of the Newton magneton. So this, so the charge is minus 1/3. Then we have the mass of the proton divided by the mass of the strange quark. And then we have the nuclear magneton. It is minus 1/3. Then we have the mass of the proton, 938 MeV. And for the strange quark, as the text suggests us, we have to use this value for the constituent mass. Okay. If you like, we can put c² here. And then we have mu n. And so when you now take this ratio and multiply by minus 1/3, the result will be minus 0.614 in units of the nuclear magneton. Okay, in striking agreement with the experimental value. Okay, so again, let me just give you the experimental value here. Minus 0.613 plus or minus 0.004. So once more, a very simple static model for the proton, or for baryons in general, okay, provides very, very good results, okay, in very, very good agreement with the experimental value. Any questions? Okay, if there are no questions, we can stop here today, and we will continue tomorrow at 11, and tomorrow we will complete this chapter about hadrons. Okay.
Ok.
Va bene, allora se non ci sono domande ci vediamo domani.
Arrivederci.
Arrivederci.
Arrivederci, prof.
Arrivederci.
Arrivederci.